Hello. Welcome, everybody. This is, I believe, our 7th IITE seminar in the series that we have on theoretical ecology, and it is my pleasure to welcome Nadav Shnerb tonight, depending on which time zone you are in, and he is going to talk about quantifying coexistence today. So without further ado, please, Nadav, the floor is yours. Thank you.
Okay, can you hear me? Fine. So thank you very much, and I thank the organizers first for the opportunity to speak here, and then for organizing this series of seminars that we enjoy for 2 months now, I think. Today I would like to describe to discuss a quantitative theory of coexistence. To do that, I will first describe what are the important quantities that we want to quantify in order to have such a theory. Then I will try to explain why the existing coexistence theory may fail in estimating these quantities. And then I will try to sketch some sort of alternative approach. Okay. So to begin, we all know that biodiversity reflects some sort of a balance between extinction and colonization. So if we have in mind some local community, say island, coupled to a regional pool by migration, then colonization is more or less, the rate of colonization is determined by some basal immigration rate, where propagules or seeds or individuals are coming from the regional pool to the local community, times the chance of invasion, which is a pi, I denote it by pi, which is a chance of a small population to grow in abundance and to reach some decent size. On the other hand, the extinction rate is mainly related to the mean time to extinction, which is the mean time needed for an already established population to go extinct. Both pi, the chance of invasion, and t, the mean time to extinction, are inherent features of the local community, while the rate of immigration, or if we think about global communities, speciation or mutation in population genetics, these are external factors that I will not discuss here. We will be interested in the stability of the parameters that govern stability of local community, maybe in the chance of invasion and the time to extinction. So what is the correct metric for such an assessment? Just in order to have a visual image in mind, I'm not going to actually consider this system. Let's think about a 3-species community that are having a zero-sum competition. So the sum of the frequencies x1 plus x2 plus x3 is equal to 1. All the coexistence states of this system lies in the interior of such a triangle, where the edges of the triangle correspond to extinction of species 3, species 2, and species 1 correspondingly. Now, how to assess stability of these systems? In the mid-70s, May and MacArthur suggested one approach. They had in mind some kind of attractive coexistence state, and they think about stochasticity as disturbances or perturbations that kicks the system out of this coexistence state, but then after the kick, the system bounces back to the coexistence state because of its attractiveness. So the measure they have, the metrics they have suggested for stability is the attractiveness that they measure by the Lyapunov exponent of the attractor divided by the strength of stochasticity. In the early 80s, Turelli criticized May and MacArthur and suggested an alternative approach. In Turelli's approach, what is important is the ability of each of the species to recover when, because of a large perturbation or disturbance, it reaches the edge of extinction. So the main parameter, according to Turelli, the main important parameter is the invasibility, the pi that we have just defined. And this is if a community is stable when all species can invade from rarity. And how to, during the years, most ecologists accept Turelli's approach or paradigm. So nowadays the coexistence theories are focused on the ability of all species to invade from rarity. How to quantify invasibility? This is usually done using the classical invasibility criterion, which is just the mean growth rate when rare. And I denote it by E, the expectation value of R, the growth rate when rare. Practically, if we have a time series of frequencies or abundances like xt, t plus delta, t plus 2 delta, and so on, where delta is some lag time, then E of R is defined as the expectation value of the log ratio of 2 consecutive points in this time series divided by delta. The main coexistence theories people are using today, like modern coexistence theory and permanence theories, are focused on E of R or equivalent or semi-equivalent properties. Now, if one wants to implement this kind of approach quantitatively, it implies that he or she takes E of R, the mean growth rate in rare, as a metric or at least a proxy for invasibility, and take invasibility as a metric or a proxy for extinction times. This is the essence of a quantitative application of this coexistence theory. However, in the last year, we questioned this approach. So what you can see here are results of a simulation of the classical lottery model with an individual-based version of the classical lottery model, where here we plotted the chance of invasion, pi, versus the mean growth rate on rare E of R, and here you can see T versus E of R. Now, by changing the underlying parameters of the model, one can find many combinations that have the same E of R, the same mean growth rate on rare. Still, they have different chances of invasion and maybe completely different chances of completely different time to extinction that may differ by orders of magnitude, meaning that the E of R, these properties are not single-valued functions of E of R. Even worse, in some cases, like the one demonstrated here in the inset, the chance of invasion may decrease as the mean growth rate on rare increases. And the same is true for the time to extinction. It may decrease when the chance of invasion increases. So E of R is not a decent metric, not for invasibility and not for existence time. And if one takes it as a metric, this is an overuse of the invasion criterion. Something that we didn't notice when we wrote this paper, but it is also true, is that we also question the Turelli's approach of taking invisibility as a proxy for existence time, because I can give up the E of R, I can just plot the time to extinction as a function of the chance of invasion, and you can see that even if I'm taking the chance of invasion as calculated from the simulation, the time to extinction may decrease as the chance of invasion increases. So these are the problems that makes the coexistence approach non-quantitative. One cannot extract quantitative parameters, the needed quantitative parameters from not from invasibility and not from the mean growth rate when rare. So the approach that I would like to suggest is a quantitative approach. What we would like to do is to calculate the chance of invasion and the time to extinction. Now there are differences between these two quantities. Invasibility is quite a universal property because all we have to discuss is the dynamics of a single population under the small population under the combined effect of all resident species and the fluctuating environment. And once you solve it for a given model, other models just imply that the effect is different, but when we solve one model, you solve all the others. On the other hand, the time to extinction, and this has to do with May and the MacArthur approach, is connected to nonlinear effects, to the details of the interaction between species, so it requires more work. Today I will show results only for invasibility, but we are now working on extinction times, and I believe that if we will be able to solve a few generic models, this will provide us a lot of insight. Now for technicalities, how to solve it. The jack of all trades in these businesses is a diffusion approximation. And indeed, Tony Dean and myself presented metrics for the chance of invasion on the time to extinction using the diffusion approximation. However, when I tried to fit the curves that I showed you in the last slide by these metrics, I find that this is not, it isn't working. And the reason is that the diffusion approximation assumes that the quantities at hand, like t and pi, are smooth over the integers, and this is not true when the environment fluctuates. So the diffusion approximation is working for fluctuating environment only if these fluctuations are very weak. We can gather some insights from this, but if we want numbers, this is not what we want to do. Instead, one has to adopt some sort of a large deviation approach. We have taken the WKB approximation as such an approach, and when superimposed on a few other tricks like asymptotic matching, we were able to solve the problem, and the details are given in this paper that will appear soon in Physical Review E. Okay, so what is our formula? For our formula, we need a few parameters that have to be extracted from abundance time series. First, I will describe what are these parameters. Then I will show you what is the formula is. And then I will explain in the next slide how to extract these parameters from a given time series. So first of all, we take a parameter like abundance or frequencies. We take the log. So we have a time series of Z, the log frequency. And then we calculate the autocorrelation time, and we define the dwell time as twice the autocorrelation time of the environmental fluctuations. So, and what we want is to verify the series such that we have a log frequency series at time legs that are the dwell time of the environment. Once we have such a time series, we can calculate the mean of delta Z between 2 points. And this mean is just the mean growth rate and rare multiplied by the parameter delta and the variance of the same quantity. The variance itself is made of 2 parts. One of them is abundance independent, and this is the environmental part that does not depend on the abundance, and demographic part that decays like 1 over n, like 1 over the abundance. So at the end of the day, we have to retrieve 3 parameters, E of delta Z, VE, and VD, the demographic and the environmental parts of the variance. Once these parameters are given, one has to calculate Q bar from these transcendental equations. We have approximate solutions for this transcendental equation that works very well. So it's not only numerics, we can proceed from this point analytically, and also the parameter R that I define here. But again, all these parameters are calculated very easily when we have E, VE, and VD. And with Q and R have to be plugged here in this formula, and this is our invasion formula. So this is the formula that gives the chance of n individuals to grow in abundance and to reach some target abundance NF before going extinct. Okay, so this is our main formula. Again, I would like now to discuss the extraction of the relevant parameters, E, VE, and VD from time series. So once we start with an abundance time series, every 2 points in the abundance time series give me 1 delta Z, which is a logarithm of the ratio between these 2 points. Once I have enough red points, enough delta Z points, I can scatter plot them against the abundance N. And find the mean. The mean is of course the mean growth rate, E of delta Z. And you can see here that the variance, the width of scatter is going down when n increases. This is because the variance is, as I said, made of two parts. One of them is environmental, that's a base variance, and the other is demographics that gives me something that goes like 1 over n. As a result, I can multiply the variance by n and plot it against the abundance. And this allows me to partition, for variance partitioning, so the intercept with the y-axis is the parameter Vd needed, and the slope of this yellow line, the slope of the growth versus n, gives me the environmental stochasticity. So that's how one can extract these three parameters from the given time series. And once these three parameters are given, we can one can plug them into the formula and find the chance of invasion. Okay, so how our formula works. So here you can see results of numerics. We have calculated the chance of a single individual to grow in abundance and to reach abundance of 200, I think, for the discrete time lottery model in an individual-based version. Here you can see many points that correspond to different parameters. The color of the point corresponds to the mean growth rate when rare, E of R, the x-axis, and the size of the point corresponds to the dwell time delta. And as you see, when I plot the results versus the mean growth rate when rare, I find some sort of cloud of points, and one can find many trajectories on which the E of R grow, but the chance of invasion decreases. On the other hand, the same points are plotted against the predictions of our formula. You can see that not only we have a data collapse, where all the points lie more or less on the same line, but the numbers are also the same. So if this is 0.03, this is also 0.03. So the formula actually predicts the chance of invasion. Here is another example from an individual-based version of the lottery model, but now it's a continuous time lottery model. So instead of killing a finite fraction of an individual each step we kill a single individual and replace it by offspring of one of the species according to their fitness. And now here I plotted pi of n as a function of n. We started with different invader populations and asked what is the chance to reach 200 before extinction. And as you can see, these filled circles are the results of a Monte Carlo simulation, and the full lines are the prediction of our formula. Again, the predictions work quite well. The fit is quite good. Something that I would like to mention here is that here we have a parameter S0, which is the mean fitness of the invader species. And you can see that even when S0 is negative, so the invader species is inferior, still the chance of invasion have the typical concave shape of a beneficial mutant or a superior species. And this is because of the storage effect that facilitates the invasion of rare populations, even if they have negative fitness. And here is the last example, now a more realistic model, the Leslie Gower forest dynamics model that was used by Jusinovich and collaborators in this paper. So here there are two equations, one for the adult trees X and the other for saplings S. And the adult trees are producing saplings at a rate Ri that is taken to be a fluctuating quantity. And now Jusinovich and co-workers provides data for this Ri from empirical measurements. So for these two tropical tree species that I will not take the risk to pronounce their names, what we did is we took their parameters, their model with the empirically calibrated fluctuating quantity here. And again, we simulated it. These are the circles, and we compare it with the prediction of the formula, which are the full lines. As you can see, the agreement is quite good. Okay, Last technical point, in many theories, people are using, in many cases, people are using theories without demographic stochasticity. When we have no demographic stochasticity, the abundance is always positive. So to define extinction, one have to put some threshold abundance below which the population is considered as extinct. And the threshold, at least I thought naively, that the threshold should be taken to be at one individual. So if the population is less than one individual, then I think that it undergoes extinction. However, when we compare our formula to results that were obtained by diffusion approximation without demographic stochasticity, it turns out that the right place to put the threshold is not at one, at abundance one, but at the abundance where the demographic stochasticity becomes equal to the effect of demographic stochasticity is equal to, it becomes larger than the effect of environmental factors and selection. So this defines the width of this red zone that one have to introduce in theories without demographic stochasticity in order to make them, adapt them to a finite world. Okay, so to summarize, I have tried to convince you that mean growth rate when rare is not a decent quantitative metric for invasibility and persistence time, that invasibility is not a decent metric for persistence time. We have a formula for the invasibility. We are still working on persistence time, but I believe that at the end, that when we will do that, we will find some sort of a synthesis between May-MacArthur approach that stresses the attractiveness of the coexistence state and Turelli approach that stresses the repulsiveness of the extinction zone. So I've already discussed these papers, so the ones where we criticized the E of R, presented the diffusion approximation and explained the WKB techniques. The advantages and the disadvantages of mean growth rate when rare were discussed in the technical comment of Steve Elner and co-workers and in our response. And I think that we reached some sort of a consensus about that. Finally, I have to thank my collaborators, so Tony Dean in Minneapolis, Ryan Chisholm and Tak Fung in Singapore. Most of the results that I have showed you here were carried with or carried by my postdoc, Jayant Pandey. Last year, I had the opportunity, a year ago, I had the opportunity to visit Steve Elner when the coronavirus was still in rarity and its growth rate was still negative. It was very fruitful. Steve showed me, explained me this historical background and the arguments between MacArthur and May and MacArthur and Turelli. And finally, the Israeli Science Foundation is paying for all this fund. So, okay, that's all. Thank you very much. And I will be happy to take whatever questions you have in mind, so assuming that I will have answers.
Thank you very much, Nadav. And if you have any questions, just raise your hand with the raise hand function in the participant list, and I will be very happy to call on you. Yes, Axel.
Thank you very much, Nadav. It's interesting. I was looking forward to your talk because I said, oh, it's very similar to what I'm doing. And it turns out it's very different. and so that made me think about the bigger picture. So one of the problems of theoretical ecology is that from an outsider, at least, it looks as if everybody is doing something else and nothing fits really together. And you may have seen, we had at least 4 previous talks about coexistence theory. We had, I think we had Guy Bunin, we had Sebastian Schreiber, we had André de Ros. I believe Stefano Alessina also talked about coexistence. And the question now is, are these just different looks, different ways to look at the same phenomenology? Or is there some fundamental disagreement about what's actually happening and therefore they don't fit together?
Well, I'm not sure that I'm the right person to comment about the large-scale structure of theoretical ecology, but from my little, small perspective, I would say that there are two questions here. One of them is more logical or fundamental, and this is how one can find systems with many species where this seems to violate the competitive exclusion principle and make complexity diversity problem, right? So why, how comes that all these species are existing together? And this is one question. Another question is, given a system and given what one can measure or extract from simulations of well-calibrated models, what may be said about the persistence properties or the coexistence properties of this system. And I think that my talk was, at least my work belongs to the second, to the later type of questions. And of course, I had in mind, and I think about it, and I worked in the past on these questions, on the possibility of feasible state with many species, given the problems of May MacArthur and Hutchinson, but this is not. I think that these are the two main questions, and the field is somewhere in between. At least, from my perspective, which is, I guess, not representative at all.
My feeling was it boils down to the question: why do species go extinct? If they are there, once they're established, why do they eventually go extinct? And you seem to suggest it's the outcome of demographic and environmental stochasticity, while other people may say, oh, it's because while they're there, some other species invades that perturbs the system, and this perturbation then leads to an extinction. The system itself changes because the species set changes, and therefore eventually one species cannot be there anymore.
Okay, but then you have to take into account the mainland in a sense, or some source. You have to have in mind some source from which new types appear, new species, new whatever phenotypes or whatever, either by migration or by mutation or by speciation and so on and so forth. I guess that these two questions happens to occur on different scales. So I didn't thought about your question in my head, but I try to make clear that in this talk, I'm looking only at the stability of a given system with its internal parameters. So I did not consider exogenous factors like immigration from some regional pool or things like that. But yes, this is something that has to be taken into account. I completely agree.
So one could maybe say what you're thinking about applies rather to isolated islands, where these things are more important, and the stuff that Yuri talked about, Guy Bunin talked about with these large species pools applies maybe more for continental patches.
Okay. When you have an island coupled, say, by migration to a mainland, and you have many species on the mainland, then depends on the parameters. So assuming that still the immigration is weak, right? Then depend on the parameters of the problem, on the interaction between species, like in some generalized Lotka-Volterra model. You can find cases where a clique of species is sort of captures the island and stays there for a long time until an immigrant from the mainland changes the situation. So you may have some sort of a glassy or a very slow dynamic behavior in terms of immigration that affects the local community. And in such a case, considerations that I presented here are relevant. On the other hand, if you have a very strong immigration of superior types from the mainland, then of course one expects that this will be the main factor that determines what is going on.
Mm. All right, thank you very much.
Yeah.
Thank you. Raul?
Very much for your talk. It was very interesting. I wanted to ask a clarification question. You present a formula for invasibility that uses species abundances, and I wanted to ask if does the formula take into account that these abundances are going to be the species that essentially were able to invade, right? That you won't see the species that did not invade. You won't, if you measure abundances, you may not capture them. Does the formula that you derive take that into account?
Well, what we applied the formula to long time series that were obtained from simulations. Okay, so many people are doing that. You calibrate some, one may calibrate a model according to the empirical findings, and then once you calibrated the model, you can run it for as long time as you want and collect results and analyze them. And in that case, there is no difference between species that are extinction prone and species that may or may not invade. It doesn't matter. You are not limited by the simulation is not a limited feature, right? On the other hand, if you want to have empirical time series, then this is a problem. I mean, because to have a very long empirical time series is something that requires a lot of work. But then actually you're right that if you have inferior species that are trying to invade, but they cannot, so their presence on the island will be only temporal, and they will disappear from the island quite fast, then it will be difficult to collect large enough empirical time series. That's right.
That makes sense. Thank you.
Thank you very much. The next one on the list was Steve.
Oh.
Hi, Nadav. Thank you very much for this talk. That's a great talk, really interesting work. I guess my question is, in a sense, a little more focused version of Axel's question about making connections. So a couple of weeks ago, we had a talk from Sebastian Schreiber, who gave us, the latest version of the invasibility one, where, we now have a very general theory that says if models without demographic stochasticity, the invasion criterion, that one number tells us everything, right? Mm-hmm. And in your case, where there's demographic stochasticity, that's no longer the case. But there ought to be a large N connection, where N is like the number of sites in the lottery model, yes. Right? There ought to be some way of taking your results and letting capital N go to infinity and recovering those results. Is there such a thing? Can you just look at your formula and say, suppose N is some small fraction of capital N and NF is some other fraction of capital N, and you let N go to infinity. Do you recover the answer that E of R tells you thumbs up or thumbs down?
Yes. So E of R is a binary classifier. Either E of R is larger than 0 or it's smaller than 0. And when compared with our formula, what you can say is that when E of R is positive, even when the destination abundance, the abundance you want to grow to, is very, very large, you still have finite probability to reach it. While when E of R is negative, the probability goes to 0. The probability to reach a macroscopic, say, very large population from small population is going to 0. This is a feature of E of R. However, when I'm saying that there is a finite chance to reach a very large population, the question is, what is this finite chance? Maybe it's 10 to the minus 5 or 10 to the minus 10. still, if E of R is positive, I know that this number is not 0, but I don't know what is the size of this number.
Okay. Well, okay, it feels like there ought to be a limit in which that probability goes to 1. I'll toss out a conjecture. If your starting point is some fixed fraction of the total,
right?
Not a fixed number, but say,
that
if your starting point is say 1% of the total number of sites,
yes,
right, and you look at this probability of going out to really large numbers, that as capital N goes to infinity, that probability should go to 1.
Yes.
Is that a valid, am I right, or am I overestimating what E of R will tell us?
I think that you are right. As far as I remember, you are right. I will double check it, but as far as I remember, you are right. Yes.
Okay.
Yes.
Okay. So that's sort of the connection between what you're saying and Sebastian is saying.
Yes, because if you have a finite population, a finite fraction of the community, when n goes to infinity, then actually if E of R is positive, you must, yes, definitely. You must you must go in abundance without limit unless you have a nonlinear effect, and you can't go extinct. Yes, definitely.
Okay.
Definitely.
Thanks.
Thank you very much. Colin is the next one.
Thanks for the talk, Nadav. That was awesome. So following up on what Raul was saying, if you were showing us results from your simulations, which was great. If you wanted to apply this to an empirical system, like obviously obtaining time series is challenging, but the plots you were showing seem to have a sort of a simulated, so somewhat ridiculous level of data points relative to an empirical study. Do you have a feel for how much you would actually need, the length of a time series you would need?
That depends very much about, first of all, about the correlation time of the environment. How much, I mean, in any case, if you want to take the environmental fluctuations seriously into account, you must have time series which is the time series should span much longer time than the correlation time of the environment. Otherwise, you actually sample only a very small fraction and non-representative fraction of the dynamics. So, I mean, and this I think is the main problem. Once you have time series that is way longer than the correlation time of the environment, then our formula should work quite nicely, I believe.
Awesome, thank you.
Thank you very much. Andre.
Yes, thank you, Nadav, for this interesting lecture. I was wondering, I mean, you showed us your formula pretty quickly, but I couldn't. I did see that somehow the denominator was something like 1 minus some quantity. Is this formula actually guaranteed to be always positive or not? Because if I take the NF very large.
Right, but then also the numerator changes sign. When the denominator becomes negative, the numerator also becomes negative.
Okay, so that's strange because if you in the numerator there was n, and in the denominator it was nf, so that can only.
Okay, so let me. Do I still share my screen, my presentation?
Yes. You just go back to the slide.
Okay.
I think it's.
So let's go to here. Okay, here is a formula, and the point is that it has to do with the sign of R. So, okay, I'm not sure that
You showed it somewhere here, yeah.
Yeah. Okay, so so the point is that when R is okay, I have to remind myself how it works. Okay, I mean, these are, we have checked, and as far as I remember, this formula cannot get negative.
Okay.
As long as NF is larger than N.
Okay.
So you subtract from one some quantity Q when, I mean, the problem is that Q bar is always negative when the mean growth rate when rare is positive.
Aha. Okay. So that's that is the connection. Yes. So it's from this this implicit condition.
Yes. When the mean growth rate when rare is positive, Q is negative, so capital R is positive. Okay. So what in the squared brackets is always positive, and when you raise it to a negative power, it is always smaller than 1.
Okay. Yeah.
So then it's always positive. And when Q bar becomes negative, then both both the numerator and the denominator changes sign.
Okay, thank you.
Thank you very much. Other question? Yeah, Robin.
Thank you. Could you bring back your slide for the effective threshold for?
Okay.
Wasn't N equals this 1? Else? No, toward the very end, when you have continuous population and you want to.
Yes, this is a slide.
Oh yes, I see it. I see that this goes down as the environmental variance goes up, and I'm wondering if you have any intuition about that.
When the environmental variance goes up, most of the phase space, the triangle, whatever you want to call it, is dominated by the selection and the environmental stochasticity and not by demographic stochasticity. That's why, and while on the other end, when the environmental stochasticity goes down, the region dominated by demographic stochasticity is much larger. So the point is that once you get trapped into the region dominated by demographic stochasticity, this is why you go extinct. Because, okay, if you have only environmental stochasticity, then you have no extinction per se, because you have either exponential growth or exponential decay, but you can go to 10 to the minus 20 and then go up back to whatever numbers that you want, right? You have no extinction. How you can get trapped into extinction, this is because demographic stochasticity if you think about stochastic processes, it's a noise that scales with the square root of the population size. This is the amplitude of the stochasticity is square root of the population size. And that's why when you get closer to zero, stochasticity with the scale with the square root of the population size is much stronger than stochasticity that scale with the population size, because the square root for epsilon, square root of epsilon is much larger than epsilon. And that's why when you go to very small numbers, the demographic stochasticity becomes dominant. And this type of stochasticity, if you think about something like Langevin equation, it sticks the system into the extinction zone. If you have a Langevin equation, you still cannot cross zero. You still have all the time you have smaller numbers. But once you get into the regime dominated by the demographic stochasticity, the stochasticity sticks the system to the to extinction. And so the dangerous zone, the zone where the system becomes, the species becomes extinction prone, is a zone where demographic stochasticity is stronger than all other effects, than environmental stochasticity and selection effects.
Thank you.
Thank you very much. Are there any other questions? Well, while we're waiting for another question to rise, I might have a question, which is that many of these things are, and this will be a question of ignorance. In many of these things remind one, and by one I mean me, who's not an expert in population genetics, of certain population genetic results. For example, this formula that's on the screen is sort of similar to the Kimura expression for probability of invasion, and even the expression for the threshold is a little bit like, where does demographic stochasticity defeat selection plus environment added in? So are these the same? Are these not quite the same?
Okay.
What's the difference?
So,
thank you.
In case where environmental stochasticity is 0, right? If VE is taken to be 0, the demographic stochasticity, in case where the environmental stochasticity is 0, our formula converges to the known expressions in population genetics that were discovered by many years ago by Kimura using the diffusion approximation, or by Haldane using the branching process theory. So our formula for invasion is exactly this, for reduces to the fixed environment formula when the environmental stochasticity is going to 0. The only new thing here is the inclusion of the environmental stochasticity. This is a non-trivial part of the story. Otherwise, yes, you're right. Everything is known.
Fantastic, thank you. And just to clarify, another difference I assume is that this formula for pi must be a little different because the Kimura formula is a diffusion approximation strictly, whereas you...
That's right, but...
it's a bit agnostic.
Okay, this is a mystery. I will be happy to learn what is the answer. For me, it's a mystery. Although the Kimura approximation, the Kimura uses the diffusion approximation, and I told you that the diffusion approximation is very limited. In kind of fixed, in fixed environment, the diffusion approximation works perfectly. I mean, this is, I have a few statements about that, but I cannot explain it. So this is kind of a miracle that Kimura used the diffusion approximation in a place that it should have quite a limited strength, but for some reason that I don't understand, in fixed environment, Kimura's formula works, very, very, very nicely, even for large selection and so on and so forth.
Well, that is very remarkable. Okay, yes. that is good to know. Thank you so much. In the meantime, are there any other questions? Okay. I assume that means no.
Yeah.
So
that's how it looks like.
Yes. No, that is fine. And so in that case, thank you so much again, Nadav, for this
talk.
Thank
you. I mean, I really appreciate this opportunity.
Thank you for coming and talking about this. So thank you, everyone. And also for the series. I believe it is so far a success. And although this is the last talk that we have for the year, we are continuing next year. The next speaker is Camille Carpentier, who's speaking on January 12th, I believe. Yeah. And then it will be Steve Elner, who is going to talk to us on the 26th. Geza, am I right?
Yes.
Yes, okay. Yes, so in other words, have a great holiday, everyone. And we're looking forward to a maybe less depressing year next year. And we hope to see you all in January in the same seminar series as usual.
Okay.
So, thank you very much and have a good rest of your year.
Yeah.